So in the last class, we were discussing about the constant phase delay and the constant group delay. And we had seen that phase delay corresponds to the delay suffered by an individual frequency. That's an individual sinusoid or maybe an individual complex exponential. And the group delay is the delay suffered by the composite signal that comprises of several sinusoids or several complex exponentials. So we had also seen that group delay is more important because the delay suffered by the narrowband signal is the important parameter and not the delay suffered by the individual sinusoids that constitutes the narrowband signal. So this comes as a continuation of whatever we had discussed in the previous session. So you need to go through whatever we had discussed in the previous session also. And we had seen that this is the figure that I'm trying to point out. For this particular case where the phase characteristic is linear and passing through the origin, you had seen that you have constant phase delay as well as constant group delay. Whereas for this one, where the phase characteristic passes through an offset, you had seen that the phase delay for different frequencies is different, and the group delay suffered by the composite signal that comprises of all the constituent sinusoids is constant. So which means the narrowband signal that is applied to the linear time varying system will come out of the system without any phase distortion. Is that clear? And we had also seen that this kind of a phase characteristics is available for a filter which has got a symmetric impulse response, and this kind of a phase characteristics is available for a anti-symmetric impulse response filter. So when the impulse response is symmetric, you have constant phase and constant group delay. And when you get an impulse response that is anti-symmetric, you see that the phase characteristics can be drawn as either crossing pi by 2 radian or crossing minus pi by 2 radian, which we have discussed in the previous class. So if I name the filter coefficients such as the phase cara passes through pi by 2 radian, then you will see that for an anti-symmetric impulse response, the phase characteristics will be a straight line, will be linear, but however it will not pass through the origin. It will pass through plus pi by 2 radian. And for this case, you will not have constant phase delay, which means the constituent sinusoids will suffer different delays. But however, the combination of the constituent sinusoids, which is your narrowband signal, will have the same shape at the output. So the shape of the output signal is preserved if the phase characteristics is linear, and whether it passes through the origin or whether it passes through a offset like this is irrelevant, because the shape of the signal will not be distorted because of phase distortion. Okay, so we will move on to 4 cases of these kind of filters which offer linear phase. The first type, which you got as type 1, is a filter characteristics, is a filter with the impulse response that is symmetric, and the length of the filter is odd. And type 2 is when the impulse response is symmetric, but however the length of the filter is even. Type 3 would be the case where the impulse response is anti-symmetric and the length of the filter is odd. And type 4 will be the anti-symmetric impulse response case with the length of the filter being even. So, and you also have to understand that when the length of the filter is odd, there will be a central sample that will be the point of the symmetry. And when the length of the filter is even, there will be a central point that is a point of symmetry or the point of anti-symmetry, and this point will be between 2 samples. So, as you'll be seeing in the presentation here, this is the case when h of n is symmetric and the length m is odd, where h of n is symmetric and the length m is odd. And I have taken care to ensure that the filter has been made possible. So this is not the zero phase response. I have a point, I have a sample about which the filter is symmetric. And this is a case where the point of symmetry is between these two samples. The length of the filter is even. The point of symmetry is between these two samples. So HFN is symmetric and M even for this case. Okay. And this is a case where HFN is anti-symmetric and M is odd. So here you have the point of anti-symmetry. And you see that the point of anti-symmetry, if there is a sample at the point of anti-symmetry, then that sample will be definitely a zero because it has to be anti-symmetric about this one. And this is a case where you have an impulse response and the length M is even, and therefore the point of anti-symmetry is between these two samples. So this is a case where M is even, right? Okay. So now comparing the symmetry and the anti-symmetry with the odd and even lengths of the filter, we can think of 4 types of linear phase FIR filters. The first you call as a type 1 symmetrical impulse response and odd M. That is length is M and the length is odd. Type 2 is when symmetrical impulse response and the length is even. Type 3 is the anti-symmetrical impulse response and the length is odd. And type 4 is the anti-symmetrical impulse response with the length as even. Okay, so we will now look at the frequency response of all the 4 types. So type 1 is symmetric HFN with M odd. So let us try to find out the frequency response of this filter. So first of all, we will start with the zero phase response H0N. So as we have seen, the zero phase response, or you can also call it as the amplitude response. The zero phase response or the amplitude response will result in a real frequency characteristics. So for example, if you have a symmetric impulse response, you will have a zero phase response which is totally real, which means there is no complex entity. So maybe this is an example of a zero phase response that is totally real. So I will mark this as -5 and this as +5. And since this is totally real, I can mark this as HR of e power j omega. So this is totally real. So we are not talking about a magnitude response in the sense that this can go both positive and negative. And we had also seen that. So this is the case where the impulse response is symmetric. For example, draw a random example. So impulse response is symmetric. Central sample is at 0. So I will mark a few other samples here like this. For example, these may be the samples that you are talking about. So maybe this is your impulse response. So 0, -1, this is +1, this is 2, and this is 3. So this is -2, and this is -3. So you have a symmetric impulse response maybe. So this is your symmetric impulse response. So maybe corresponding to this symmetric impulse response, I have a frequency response which we have seen in the previous class as purely real. So when the symmetric impulse response is purely real, I can maybe represent a random example like this. So to make this causal, I have to shift this by 4 samples. So 3 samples to the right, so that this is now causal. So which means now I can relabel the indices as, say, for example, if I shift this by 3 samples to the right, I can mark the impulse response like this now. This is a sample at 0. So sample at +1 would be this one. Sample at +2 would be this one. Sample at +3 would be this one. This is sample at +4. Sample at 5. And your sample at 6. So these are your samples. So samples are 0, 1. This is 1, 2, 3, 4, 5, and 6. So there are 7 samples, so which means m is equal to 7. And the point of symmetry is at m minus 1 by 2. So the point of symmetry is at m minus 1 by 2, which is equal to 3. So this is where you have your symmetry. So for the zero phase response, the symmetry is at the origin, right? So this is your HR of e power j omega. And now when this is shifted by 3 samples, it is equivalent to adding a phase response like this. Is equivalent to adding a phase response like this. So you are interested only from minus pi to plus pi because those are your digital frequencies. So maybe this is your phase response that we have. This is the phase response, and the slope of this line would be 3 because you have shifted by 3 samples. So this is omega, and this is 0. This is theta of omega. So now very easily you can appreciate why we have a amplitude response instead of a magnitude response. If we had drawn the corresponding magnitude and phase response, it would not have been as easy to appreciate the linear phase response of the filter. So for example, let us try to draw the magnitude response in this case. The magnitude response would be magnitude response you need to mark from minus pi to plus pi. So magnitude response should be something like this. So this will be your magnitude response. This is minus pi, this is plus pi. Now, which means that the phase response will be equal to minus pi. So this is originally negative. Now, when you take the magnitude, this is turning positive. So which means here you have a phase response equal to minus pi radian. And this is negative here, whereas the magnitude is positive, which means you have a phase response of plus pi radian. Now, along with that, you have to add the linear slope. So I will, first of all, I will mark the phase angle corresponding to the magnitude response, and then to that I will add the linear phase because of the shift. So you see that in this region, you mark the angle as positive, and in this region, you mark the angle as negative because it is plus pi radian here, and this is minus pi radian. Now you are shifting this so that the entire impulse response is made positive. So which means you have to add use a different color to indicate that. So here you are adding this line to 0. So here there is no angle to speak of. So in this region it will be like this. So this is the angle in this region. And here you are adding a plus pi. So you have a jump here. And from here it will continue. And here you will have again a jump. And from here it will continue like this. So this is not easy to appreciate. So the linear characteristics is not easy to appreciate with this kind of a phase response. Whereas the phase response is easier to represent with the amplitude response instead of the magnitude response. So that is the significance of the magnitude response of the zero phase response. Okay, so we'll go back to the presentation now. So the zero phase response is when the symmetric impulse response is centered about the origin. So you have a sample at 0, so which we call as H0, and you have samples at plus or minus 1, which we call as H01 and H0 minus 1. You have sample at H02 and minus 2, and so on. And the samples, last pair of samples will be H0 of m minus 1 by 2 and H0 of minus of m minus 1 by 2. So these samples are on the positive side, these samples are on the negative side. And therefore, if you compute the zero phase response, you can compute the zero phase response by using the DTFT equation as follows. So that would be H0 of 0 into e raised to minus j omega 0, that would be H0 of 0, plus H0 of 1 into e raised to minus j omega into 1, so that is e raised to minus j omega, plus H0 of minus 1 into e raised to minus j omega into minus, which is e raised to plus j omega, plus so on, etc. Now note that H0 of 1 and H0 of minus 1 are the same. H0 of 1 and H0 of minus 1 are the same because this is a symmetric impulse response. So these two can be combined. E raised to j omega and e raised to minus j omega can be combined. Likewise, we can combine e raised to j2 omega and e raised to minus j2 omega and so on. So when this is combined, e raised to j theta plus e raised to minus j theta is, what is that? It is 2 cos omega. This is 2 cos omega. This will be 2 cos 2 omega. And this would be, if you combine these two, because these two are the same, this would be H0 of m minus 1 by 2 into 2 cos m minus 1 by 2 omega. So if you combine in this fashion, you can write HR of e power j omega, which is the amplitude response, which is real. That is why we have the suffix HR. HR of e power j omega can be written as sigma n equal to 0 to m minus 1 by 2 a of n cos omega n, where a of 0 is equal to H0 of 0, and in general a of n for other than n equal to 0 can be written as 2 into H0 of n, which is also equal to 2 into H0 of minus n because of the symmetry. Now this is your zero phase response. We have to make this causal. How we will make this causal? By shifting by m minus 1 by 2 samples to the right. By shifting by m minus 1 by 2 samples to the right. So that now the symmetry would be at m minus 1 by 2 and out at 0. So the zero phase response has to be made causal and has to be delayed by m minus 1 by 2 samples. Therefore, h of e power j omega can be written as h of e power j omega is the frequency response of the filter that has been made causal, as which is equal to HR of e power j omega into e raised to minus m minus 1 by 2 into j omega, which we can write as h of e power j omega. So if you substitute for HR of e power j omega, you can write this as h of e power j omega is equal to sigma n equal to 0 to n minus 1 by 2 a of n cos omega n into e raised to minus m minus 1 by 2 j omega, where a0 was originally H00, which now appears at h of m minus 1 by 2. So a0 is h of m minus 1 by 2, and a of n would be, originally this was at 2 h0 of minus n, this was 2 h0 of minus n. That would be therefore 2 h of m minus 1 by 2 minus n, because it has been shifted by m minus 1 by 2 samples. Right? So this is the case where the symmetric response is impulse response is symmetric and the length of the filter is odd. You see that h of e power j omega comprises of a real amplitude response and a linear phase response. a real amplitude response and a linear phase response. So this is important. This is illustrated graphically here. Earlier, this is H is ref. The point of symmetry is at n equal to 0. Samples are from minus and minus 1 by 2 to plus and minus 1 by 2. You had computed the amplitude response or the zero phase response for this filter. And now this has been shifted and made causal. So the point of symmetry is now at minus 1 by 2. So you have a sample at the point of symmetry. So this is the filter that we are talking of now, which comprises of a amplitude response and a linear phase response that passes through the origin. So for this case, you will have constant group delay and constant phase delay. Constant group delay and constant phase delay. Okay. So we will now move on to the type 2, which is symmetric H of n with the length of the filter as even. So when the length of the filter is even, you have to understand that when the length of the filter is even, you have to understand that there is no sample at the point of symmetry because the point of symmetry will be between two samples. So let us illustrate this using the whiteboard. So let me start with some impulse response. I will draw this as a symmetric impulse response with even number of filter coefficients. So let us say as an example 4. So even number of samples. So which I am going to mark like this now. So what I'm doing is I don't have a sample at 0, but I have a sample on either side of 0. I don't have a sample at 0. So two samples, maybe these are my samples. And now see that this is separated by half sampling interval. So I will mark this as minus half because it is shifted by half sampling interval. And this I will mark as plus half. Why I am doing it like this, it will become clear now, sure. And this should be therefore 3 by 2, and this is minus 3 by 2. So I have 4 samples here. So this is shifted by, this is spaced apart by one sampling interval. These two are spaced apart by one sampling interval, and these two are spaced apart by one sampling interval. Say for example, I might have a filter as shown here, 3, 4, 4, 3. Maybe this is my filter that I'm going to look at. And this is where I would be having my origin. Maybe this is my original filter, which is a causal filter. I'm going to make this as follows. So like this, maybe if I move this by 2 samples to the right, now I have a filter which is represented like this: 3, 4, 4, 3. Maybe these are my 4 samples. Let me mark the origin here. So the origin is marked somewhere here. This is where I have marked the origin. So I have samples from, what is this? This is 0, this is 1, this is minus 1, and this is minus 2. And here the length of the filter was equal to 4. Now you see that this filter, if this is how I am going to represent, so I am going to mark the origin at the second 4 here. Okay, so this is how I'm going to mark the 0 phase signal. This is not exactly 0 phase now, so I've just shifted this by 2 samples right. So in general, I can say that one will come, one will be equal to m by 2 minus 1. In general, this will be m by 2 minus 1, and this will be minus m by 2, right? So the samples will be from minus n by 2 to m by 2 minus 1. So I have taken more number of negative samples and one lesser number of positive samples in the positive index. So more number of samples on the negative side and one less number on the positive side, like this. See, for example, I start from I don't have a samplet. If I start from 0, then I will have m by 2 samples here. If I start from -1, I will have m by 2 samples here. Is it clear? So there are more number of samples with negative indices than samples with a positive indices. Or I can say the number of samples with positive index is 1 less than the number of samples with negative index, right? So this is now 3, 4, 4, 3. So because you don't have the concept of this shifting by half sample, this you have to be very careful of. So how will I make this zero phase? For this, I have to again shift this by half sample to the right. So if I have to again shift by half sample to the right. So 3, 4, 4, 3. This is where I'll be having my sample now. My point is symmetry now. So this will result in a labeling of the index in this fashion. So here I will have 0. This will be plus half. This will be plus 3 by 2. Therefore, this will be minus half, and this will be minus 3 by 2. Therefore. So we have a kind of renaming of the filter indices. Okay. So now we'll go back to the presentation. So starting with the shifted response. So what we'll do is we'll shift the anti-symmetric impulse response to the left, such that the indices are from minus m by 2 to m by 2 minus 1 as indicated. And we will relabel the indices of H0 of n, which are originally from minus m by 2 to m by 2 minus 1, by a shift of half samples to the right. So which means the samples will be from minus m minus 1 by 2 to m minus 1 by 2. So the samples will be from minus m minus 1 by 2 to m minus 1 by 2. See that m is now even. So therefore m minus 1 is odd. So minus m minus 1 by 2 will be a multiple of 1 by 2. And m minus 1 by 2 also will be multiple of 1 by 2. Which are exactly odd multiples of 1 by 2. So which means the original index 0 will have a sample H is of half. H is of half. Then you will have H is of minus half. Likewise, m by 2 minus 1, the sample at m by 2 minus 1 will be H is of m minus 1 by 2. And the sample at minus m by 2 will be now at minus m minus 1 by 2. And we will label that sample as H is of minus m minus 1 by 2. So now we will find out the real amplitude response. So again, let us go back to the whiteboard. You see that now this is now symmetry, as the indices have been relabeled as odd multiples of 1 by 2. So since the indices are relabeled, now this is a symmetric impulse response, and therefore you will end up with a real frequency response. Say for example, you don't have a sample at 0, so but you have a sample at 1 by 2. So maybe we can write this as h instead of 1 by 2 into e raised to minus j omega into 1 by 2. See? So h instead of 1 by 2 into e raised to minus omega 1 by 2 plus h instead of minus 1 by 2, which is same as h instead of 1 by 2. So h instead of 1 by 2 into e raised to plus j omega 1 by 2. So which these two can be combined in the form of a cosine function like this. Likewise, these two also can be combined in the form of a cosine function. These two also can be combined in the form of a cosine function. Okay. So now we'll go back to the presentation. So h is of 1 by 2 plus h is of minus 1 by 2 e raised to j omega. Since you have to shift this by half samples, you are shifting this by half samples to the right, which means you have to multiply this by e raised to minus j omega 1 by 2. So h is of 1 by 2 was originally at the index 0. So that would be h is of 1 by 2 into e raised to minus omega 1 by 2. So I'm taking this h is 1 by 2, which is originally at 0. So this is to be multiplied by e raised to minus omega 0. So that will be h is 1 by 2 itself. Now h is of minus 1 by 2 is originally at the index minus 1. So it has to be multiplied by e raised to j omega. H is of 3 by 2. H is of 3 by 2 is originally at the index 1 and therefore it is multiplied by e raised to minus omega. And h is of minus 3 by 2 is originally at the point of minus 2 and therefore multiplied by e raised to 2j omega plus etc. And h is of m minus 1 by 2 is originally at the index m by 2 minus 1 and therefore multiplied by e raised to minus j omega into m by 2 minus 1. And h is of minus m minus 1 by 2 is originally at the index minus m by 2 and therefore has to be multiplied by e raised to j omega into m by 2. And the entire thing has to be shifted by half sample to the right. So I will multiply this by e raised to minus j omega into 1 by 2. Right? So this is multiplied by e raised to minus j omega into 1 by 2. So this I will group like this. So this we can write as 2 h is into 1 by 2. So if I take this inside, e raised to minus omega half, this would be e raised to plus j omega half. This would be e raised to minus j omega into 3 by 2. And this would be e raised to plus j omega into 3 by 2. Likewise, this would be e raised to j omega into m minus 1 by 2. And this would be e raised to e raised to minus j omega into minus 1 by 2. And this would be plus e raised to j omega into minus 1 by 2. So combining, I can write this as 2 h is of 1 by 2 into cos 1 by 2 omega plus 2 h is of 3 by 2 into cos 3 by 2 omega plus etc. up to 2 h is of m minus 1 by 2 into cos m minus 1 by 2 omega and represented as sigma n is equal to 1 to n by 2 b of n cos omega n minus half, where b of n is 2 h is of n minus half. So see that this turns out to be entirely real. So HR of e power j omega is a real, it's a real amplitude response. Now this has to be made causal. How will you make this causal? You have to delay this by m minus 1 by 2 samples. See, as in the example that we have here, this has to be delayed by 3 by 2 samples. What is 3 by 2? 3 by 2 is m minus 1. M is 4. 4 minus 1, 3. 3 by 2 samples. So this has to be delayed by 3 by 2 samples. When it is delayed by 3 by 2 samples, the entire impulse response becomes now causal. So h of e power j omega would be therefore hr of e power j omega into e raised to minus omega m minus 1 by 2. E raised to minus omega and m minus 1 by 2. That is h of omega can be written as sigma n is equal to 1 to n by 2 b of n cos omega n minus 1 by 2, which is what we had earlier, which is hr of e power omega, to be multiplied by e raised to minus omega n minus 1 by 2, where b of 1 is 2h is of 1 by 2, which is also equal to 2h is of minus 1 by 2, which is equal to 2h of n by 2 minus 1 in the shifted causal sequence. And in general, you can write b of n is equal to 2h of m by 2 minus n, where n is equal to 1, 2, etc. to m by 2, right? So this is the example. This is your h is of n, and this is your h of n. Earlier, the symmetry was at the origin. Samples were labeled as minus 1 by 2, plus 1 by 2, minus 3 by 2, etc. And now the samples are labeled as 0 to m minus 1, right? Okay. So, therefore, you can write h of e power j omega is equal to sigma n is equal to 1 to n by 2 b of n cos omega n minus 1 by 2 into e raised to minus j omega n minus 1 by 2, where b of n is equal to 2 h of n by 2 minus n, where n is equal to 1 to x to n by 2. So what does it mean? You have a linear phase response here that passes through the origin. the slope of the linear phase response is m minus 1 by 2 because it has been delayed by m minus 1 by 2 samples, and this turns out to be a real amplitude response. This turns out to be a real amplitude response, right? So this is the type 2 sequence, type 2 filter. Now we will move on to the type 3 filter. And we have seen that the type 3 filter is an anti-symmetric impulse response filter, and the length of the filter is odd. So you have a point of anti-symmetry where it passes through zero. The impulse response value of the sample at the point of anti-symmetry has to be definitely equal to 0, which we have discussed earlier. The central sample is a 0. Now we will start by making this anti-symmetric with respect to the origin, because the length of the filter is odd. We have to think of an anti-symmetric filter where the length of the filter is odd and the point of anti-symmetry is at the origin. So let us consider an example like this. So the length of the anti-symmetric filter is considered to be odd here for our example. So let us look at 5 samples. So I'll draw only positive samples on the positive side, and these are my negative samples. Okay. So the indices are at, let's say this is 0, this is 1, this is 2, this is 3, and this is 4. So now we will start by moving these 3 samples to the left, so that you can think of a anti-symmetric impulse response, which is anti-symmetric with respect to the origin. I will just relabel the indices therefore as follows. Relabel the indices now. The indices are at 0. This is 1, 2, and -1 and -2. See that the sequence is anti-symmetric with respect to the origin. So this is a sequence which has been made anti-symmetric with respect to the origin. Let us put some numerical values here, so that this is, let me say this is -4, this is -3, this is 0, this is +3, and this is +4. So the filter that I was originally talking about was -4, -3, 0, 3, and 4. This was the original anti-symmetric filter that is a causal anti-symmetric filter that I had originally. And now by shifting this by 3 samples to the left, I put the origin at the, sorry, the original anti-symmetric filter had the 0 index here. This was my causal anti-symmetric filter, which I have made symmetric with respect to the origin by moving this by 3 samples to the left. So -4, -3, 0, 3, 4. So this is where I have the origin. This is the original sequence, and by shifting this by 3 samples to the left, we have made the point of anti-symmetry at the origin. So this is where I have the point of antisymmetry, and now the point of antisymmetry is at the origin, right? And you have seen that well, if you label this as this is h of 0, this is h of 1, this is h of 2, h of 3, and h of 4. You see that for this example, h of 4 is equal to minus h of 0. H of 3 is equal to minus h of 1. And we have another h of 2 also. So therefore, the frequency response can be written in this form. That is h of 0 into e raised to j omega 0 plus h of 1 into e raised to minus omega 1 plus h of 2 into e raised to minus omega 2 plus h of 3 into e raised to minus omega 3 plus h of 4 into e raised to minus omega 4. Right? So this is how we relabel this. Now, for this sequence, which has been made symmetric with respect to the antisymmetric with respect to the origin, the frequency response should be something like this. H of 0, this is the original h of 0. H of 0 is now at this position. So h of 0 into, now it has been, it is now located at minus 2, right? So h of 0 into e raised to j omega 2 plus h of 1. The original h of 1 is here. Now it is located here. So h of 1 into e raised to j omega 1. Then we have a 0 here, so nothing here. So minus h of 1 into e raised to minus j omega. And finally I have minus h of 2 into e raised to minus 2j omega, right? So which we can now group as follows here. So here we can write as h of 0. I'll just take this upwards. So this we can write as h of 0 into no, this is h of 0. So h of 0 into e raised to j omega 2 minus e raised to minus j omega 2 plus h of 1 into e raised to j omega minus e raised to minus j omega, which can be written as h of 0 into 2j sine 2 omega plus h of 1 into 2j sine omega. All right, is it understood? So I will take this 2j outside. So I can write this as 2j h of 0, 2j into h of 0 into sine 2 omega plus h of 1 into sine omega. You see that this is entirely real. This part is entirely real. So I can maybe into 2, that is also real. So maybe I can write as an HR of e power j omega, which is totally real, multiplied by a j, which we can write as angle pi by 2 radian. So this is HR of E for j omega into angle pi by 2 radian. I have discussed this for a case where the length is equal to 4. So you can appreciate that this can be extended to any example where the length is an even number. So let us go back to the presentation here. This is the case of antisymmetric H of M over. So we start with a zero phase response H is of n. So note that the central sample is a 0. So instead of HR of omega, I will call this as HI of omega because this will turn out to be purely imaginary. So HI of omega is equal to minus H is of minus 1 d raised to minus omega plus H is of minus 1 d raised to j omega as before, as for the example that we had seen. Finally, which you can write as j into 2 H is of minus 1 into sine omega. So I've chosen to represent this in terms of minus 1. 2 H is of minus 1. So in terms of H is 2 H is of minus 1 into sine omega plus 2 H is of minus 2 into sine 2 omega plus etc. up to 2 H is of minus m minus 1 by 2 into sine m minus 1 by 2 omega. We will group it like this. So HI of e power j omega, because it turns out to be purely imaginary, HI of e power j omega can be written as equal to sigma n is equal to 1 to n minus 1 by 2 c of n sine omega n into e raised to j pi by 2 radian. So which means you have a part that is totally real. So this part is totally real, and this real part is multiplied by j. So you have a zero phase frequency response as shown, as will be shown in this on the whiteboard now. The zero phase response may be represented like this. So we have some HR of e power j omega, so which will maybe represent like this. So this is minus pi and this is plus pi. So this is the term corresponding to, this is the plot of sigma n equal to 1 to n minus 1 by 2 c of n sine omega, which is purely real. This will also have this phase e raised to j pi by 2 radian. So the phase angle will be identically pi by 2 radian through. So I will use a different color to represent that, maybe using a green color. The phase angle is uniformly pi by 2 radian. So this is pi by 2 radian. So pi by 2 radian. So this will be the frequency response of the filter that has been made antisymmetric with respect to the origin by shifting the samples by m minus 1 by 2 to the left, so that the original causal filter is now symmetric with antisymmetric with respect to the origin. Okay. So we'll go back to the presentation here. So HI of e power j omega can be written as sigma n equal to 1 to m minus 1 by 2 c of n sine omega and e raised to j pi by 2 radian, where c of n is equal to 2 h z of minus 2 h z of minus. So what we will do is now, this is the amplitude response. Amplitude response can be written as sigma n equal to 1 to m minus 1 by 2 c of n sine omega n. Now the zero phase response has to be made causal and has to be delayed by m minus 1 by 2 samples. So therefore h of e power j omega can be written as hi of e power j omega into e raised to minus m minus 1 by 2 into j omega. So which is written like this. H of e power j omega into, this is your amplitude response, multiplied by, you have to take into account this additional phase and the e raised to j pi by 2 previously. So this becomes e raised to j pi by 2 minus m minus 1 by 2 omega, where c of n is 2hf and minus 1 by 2 minus n. So let us go back to the whiteboard. So what this will finally end up is a phase response which is linear, but sorry, which is linear but passes through pi by 2 radian instead of through the origin. It passes through pi by 2 radian. Maybe this is your phase response. For the example from this is your phase response. So this filter has got a linear phase carrier, but that linear phase carrier does not pass through the origin. But instead it crosses the y-axis at a pi by 2 radian. So which means you will now have constant group delay and the phase delay will be varying. You will really have constant group delay. So when you have an anti-symmetric impulse response, you will really have constant group delay. You will not have constant phase delay. So which means that if you have a composite signal, say for example, some random signal which I am drawing here, this is applied to a linear time invariant system as an input. And the output, I will have a signal that is same as that of, that has the same shape as that of the input, except that it will be delayed. This will be the, if this is the input, this is the output. Okay. If this is a narrowband signal, the same narrowband signal shifted by a delay will appear at the output for this kind of a system. However, the individual frequency components of this composite signal will suffer a different phase delays. You are not at all bothered about the delay suffered by the individual sinusoidal components, but however you will ensure that the shape of the signal is preserved at the output, provided that this is a narrowband signal. Shape of the signal is preserved at the output. Is that understood? Okay. So right now we will now therefore move on to the fourth type of filter. That is the type 4 anti-symmetric H of an M even. So the derivation is exactly like the type 2 filter, except that now you have an anti-symmetric impulse response. So starting with the zero phase response, which is originally from minus m by 2 to m by 2 minus 1, by a shift of half samples to the right, so that it is now from minus m minus 1 by 2, which is an odd multiple of 1 by 2 to m minus 1 by 2. Now we have h instead of 1 by 2, origin index 0, h instead of minus 1 by 2, origin index minus 1. Likewise, it increases. So therefore, you can write the HR expression for HR of E for omega as h is of 1 by 2 plus etc. into e raised to minus omega 1 by 2, because you have to shift this by half samples to the right. Just like we relabeled the indices previously, we have to shift by half samples to the right, so that now it is anti-symmetric with respect to the origin, and there are two samples on either side of the origin. So you don't have a sample at the point of anti-symmetry. Instead, the point of anti-symmetry is between two samples. And finally, you will end up with an expression like this. HR of e power j omega is sigma n equal to 1 to n by 2 d of n sin omega n minus 1 by 2. Because of this j time, you will have an e raised to j pi by 2. See that you have sin omega n minus 1 by 2. Just like for your type 2 filter, where it was cos omega n minus 1 by 2, now you have sin omega n minus 1 by 2 into e raised to j pi by 2, where d of n is obtained like this. So therefore, the frequency response of the causal filter, therefore the frequency response of the causal filter is obtained by delaying this by m minus 1 by 2 samples. So therefore, you can write h of e power j omega is into hr of e power j omega into e raised to minus omega m minus 1 by 2, and h of e power j omega is therefore sigma n equal to 1 to n by 2 d of n sin omega into n minus 1 by 2. This part turns out to be purely real. This turns out to be purely real, and this is e raised to j originally you had pi by 2. So pi by 2 minus omega into n minus 1 by 2. So it will cross the y-axis at pi by 2 radian, where d of n is equal to 2h of n by 2 minus n for n equal to 1 to h of n. See the indices, summation of the indices is from 1 to n by 2. Okay. Okay. So these are the 4 filters that we have seen. Now we will see certain peculiarities about the 4 filters. The peculiarities are as follows. The type 1 filter is a symmetric filter with the odd number of samples. Type 1 filter can be used to design all kinds of filters. You can use type 1 filters to design high pass, low pass, band pass, and band stop filters. But however, for the other types, types 2, type 3, and type 4, there are certain restrictions. As we are going to see now, the type 2 filter has got a frequency response as follows: h of e power omega equal to sigma n equal to 1 to n by 2, b of n cos omega n minus 1 by 2 into e raised to minus omega n minus 1 by 2. And you see that because of this 1 by 2 term here, let us see, let us go to a whiteboard and see what is the effect of that 1 by 2 term. Now you know that the filters, low pass, high pass, band pass, and band stop filters in the discrete domain are to look like this. This would be a low pass filter in the discrete domain. I will draw ideal filters. So this is your low pass filter in the discrete domain. So this is minus pi, and this is plus pi, and I will mark this as omega c, and this is minus omega c. So which means you have a pass band between minus omega c to omega c. It's a real filter, so that is why you have a symmetric frequency response here. And the stop band is for mod omega greater than omega c, right? Mod omega greater than omega c. So mod omega greater than omega c, but less than pi. So mod omega will be between omega c and the pi. So that is your stop band, because your constant of frequencies will be between minus pi and plus pi. Now let us look at a high pass filter. Let us look at what a high pass filter will look like. The high pass filter now will be just the reverse. This is your high pass filter. So this is minus omega c plus omega c. This is plus pi. This is minus pi, right? So this is your high pass filter. Likewise, what would be a band pass filter? I draw my band pass filter here. My band pass filter would be from a cutoff frequency omega c1 to a cutoff frequency omega c2, both of which are less than pi radian. So this is pi radian. This is, we have, since it's a real filter, you will have a symmetric magnitude response. So this is minus omega c1, this is minus omega c2, and this is minus pi. So this is your band pass filter. I have drawn ideal band pass filters. Likewise, let me draw my band stop filter. So you have two frequencies, omega c1 and omega c2, and the filter is supposed to stop all frequencies in between omega c1 and omega c2 like this. Okay. Likewise here also, between omega c1 minus omega c1 and minus omega c2, the filter stops the frequencies, filter stops the signal, and this is the ideal band stop filter. So we will need this for our discussions. Let us go back to the presentation now. Let us look at the type 2 filter. The type 2 filter has got this 1 by 2 cos omega n minus 1 by 2 type term. So let us look at what is the value at omega equal to pi. Omega equal to pi will mean pi into n minus half. So cos pi into n minus half. Let's put as an example n equal to 3. So cos pi into 3 minus half. Cos pi into 3 minus half would be cos 5. So let us put cos. This would be cos omega into n minus half. So if you put cos pi into 3 minus half, that would be cos 5 by 2 pi omega. Cos 5 by 2 pi. So cos 5 by 2 pi is equal to 0. So if you put omega equal to 0, if I put omega equal to 0, that will be cos 0, which is equal to 1. If I put n equal to 0, that will be cos pi into minus 1 by 2. That will be cos minus pi by 2, which is equal to 0. Right? So if I put omega equal to pi or omega equal to minus pi, all these cosine terms will vanish to 0. Because cos pi by 2 is 0, cos 3 pi by 2 is 0, cos 5 pi by 2 is 0, cos minus pi by 2 0, cos minus 3 pi by 2 0, etc. So for omega equal to plus or minus pi, you see that this amplitude response vanishes to 0, right? So definitely for type 2, the amplitude response vanishes to 0 at plus pi by 2 and minus pi by 2. So for low pass filters, it is okay because it has to vanish to 0 at plus pi by 2 and plus pi and minus pi. So obviously low pass filter can be designed. But the high pass filter cannot be designed because of the type 2 filter, the frequency response becomes 0 at omega equal to plus pi and omega equal to minus pi, right? And for the band pass filter also, it seems to be okay because it can reduce to 0 at plus pi and minus pi. However, for the band stop filter, this cannot have a non-zero value at plus pi and minus pi. So therefore, you cannot design high pass filters and band stop filters with the type 2 kind of filters, right? At omega equal to pi, HA of e power j omega equal to 0, which signifies that you cannot use type 2 to design high pass or band stop filters. Now for type 3, type 3, you have this term sine omega n. Since you have sine omega n, you see that at omega equal to 0, sine 0 is equal to 0, and at omega equal to pi, at omega equal to pi is also, that's also equal to 0 because sine pi n, that becomes equal to 0. So therefore you cannot have non-zero values at omega equal to 0 and omega equal to pi for the amplitude responses, which means that you cannot design low pass filters. And because at omega equal to 0, the value has to be equal to 0. At omega equal to pi also the value has to be equal to 0. So the high pass filters are also counted out. You cannot design low pass filters. You cannot design high pass filters, and likewise you cannot also design band stop filters because at omega equal to 0 and at omega equal to pi, the frequency response has to return 0 value. The only kind of filter that you can design is your band pass filter, and we will see later that you can design only Hilbert transformers and differentiators. You can design Hilbert transformers and differentiators, which are special kinds of band pass filters, which we'll be discussing later when we see design of FIR filters. Right? Okay, we'll move on. And now for type 4 also at omega equal to 0, only at omega equal to 0, you cannot design filters that have non-zero value at omega equal to 0, which means you cannot design for low-pass filters or for band stop filters, low-pass filters or for band stop filters. And now the type 4 filter has got a zero phase response of this filter, which is purely imaginary. Type 4 filter can be used to design Hilbert transformers. You cannot design perfect Hilbert transformers in the discrete domain. You can only design approximation to Hilbert transformers in the discrete domain. Whereas the type 3 filters can be used for Hilbert transformers and differentiators. You will later see that for designing differentiators, you have to look at definitely specifically type 3 filters. You will not use type 4 filters for designing differentiators. We will discuss all that in the next session. We will stop this for now. We will continue afterwards. Maybe today itself I will record a session and then I will upload. Thank you.